Hello everyone, I'm Kungmin Lin, currently an undergraduate student at UC Berkeley. Today I'm going to present OpenUVR, an open source system framework that makes high quality, low cost, untethered virtual reality gaming possible with commodity hardware components. We achieve less than 20 milliseconds virtual latency between a gaming desktop computer and Raspberry Pi based user client for a first person shooter game with HD resolution. I worked on this project when I was a high school student intern at Extreme Storage and Computer Architecture Lab at UC Riverside under the advising of Professor Hung-Wei Tseng. This project is done with other lab alumni, Alec Rohloff, Zackary Allen, Joshua Okrend, and Chengyi. So I'm sure all of you have seen and interacted with, or have at least heard of, a VR. There are many VR applications, whether it is for gaming, simulations, or military training. But if you have experienced one of these before, the experience might have looked something like the left, where the headset is so heavy in the front that it is difficult to hold your head upright without hurting your neck. The more common scenario is the image on the right, where the wires just get in the way of your immersive experience. So let us discuss the general architecture behind these common VR headsets. The first one would be the wired design, which is the most common one. Having a wired configuration means that the latency is low enough for our application to be hosted on a PC or a more powerful machine. This would also lead to high performance, but the mobility of our user will be restricted by the wire. You must have seen wireless, or what we call untethered VR products on the market. These headsets typically host their own VR application with rendering, processing of inputs and outputs, all done on the same client device. Although these devices could use the cloud to store most of its memory, its performance is still limited. And I would argue the mobility aspect is not much better, provided that the device would still be heavy with the hardware required to host and render VR applications. Now, the obvious solution to all of this is taking the wired architecture and replace the wire with wireless links. While that does address the issue of mobility and performance, the wireless link becomes a huge source of latency. Latency is not an issue to be underestimated. The reason why products on the market has evolved in the direction of the first two architectures is because latency has a much more drastic consequence on the user. There are multiple studies published on motion sickness induced by latency in the head-mounted display, and it has been established that a threshold of 20 milliseconds has to be achieved in order to prevent motion sickness. In other words, VR applications can be considered as real-time applications, as these applications must fulfill the following two characteristics. One, from user input to the display output will only have 20 milliseconds. And two, the result passed through, or say a frame that is earlier than the current frame, is completely meaningless to the user. And to measure the total latency between the host PC and the user device, we compare the timestamps shown on the display of these two machines. We use high-speed photography to view the difference in timestamps. While running a video game called Unreal Tournament, here's what we found. Untethered VR systems today that uses the third configuration we discussed all fail at meeting the 20 millisecond threshold. And let's see why that is. So most modern systems are designed to be throughput oriented. This even includes popular communication network standards like Wi-Fi. Their specifications only mention or care about throughputs. That is, the number of bits that the media can carry within a given time frame. But this system disregards latency, the time it takes for the data to travel from the server's network stack to the client. As a result, modern network protocols spend a significant amount of time in their system stack, accounting almost 50% of the end-to-end latency in sending a frame, instead of spending most of that time on the wireless media. In addition, the system also spends significant amount of time in encoding video on the host PC. So let us first take a look at the video encoding. There are multiple layers involved with this process. The largest contributor to latency here is the conversion from the RGB format to the YUV format, which enables efficient compression without much loss in video quality. Despite its advantages, conversion to the YUV format requires access to the raw RGB content, which we see right here. Latency from the color space conversion and buffering is helpful in conventional video streaming applications in making video quality stable and reducing the network traffic, but not in the case of latency-sensitive VR applications. So in OpenUVR, we tackle this problem by eliminating the color space conversion. Instead, we utilize the GPU's hardware-accelerated encoder to directly compress VR content in native RGB format, simplifying the system stack to the diagram you see here. What's more, there's no longer a need to capture the game video, since the contents are made visible in the shared GPU memory space of the VR game in the OpenUVR module. And this first step of optimizing video encoding results in a significant reduction of latency already. We measured a 3.75 times speedup in this process between the two models on the same device. Similarly, there is a lot of layering involved in the wireless network subsystem, which causes overhead. So let us take a look. After the encoding phase, the traditional wireless VR framework streams content into the network stack's transport layer, and then the data passes through the network layer and the data link layer before it is ready for transmission in the network interface hardware. In each network layer, a protocol-specific header and checksum are attached, and the data is repartitioned into the layer's protocol-specific format. This requires CPU processing and multiple main memory buffers, increasing network latency on the host PC. To address this, we implement parts of the OpenUVR content capturing and presentation modules as system kernel modules. This allows us to remap main memory locations used by the game to physical memory locations used by the network stack. In addition to eliminating memory accesses in between network layers, we actually reduce the number of layers by using the peer-to-peer network topology and directly generate the MAC layer packet, bypassing the network and transport layer. This strategy comes with many benefits. First, it eliminates the one-hop delay on the wireless base station, which could cost a few milliseconds. And the P2P model also prevents a datagram from going through wireless channels in the same area twice, since the host PC and the head-mounted display typically share the same access point, as is the case in the Hua Gaming Anywhere VR. With these improvements, we have a 4.46 times speedup in the host PC's network stack. And if we add up all of these latencies, we get a total latency that is well below the 20 millisecond threshold. The network stack on the client is also reduced as a result of opting for a P2P network. In total, compared to the Hua Gaming Anywhere VR, we have reduced end-to-end latency by 25,134 nanoseconds. So to show you the real user experience of OpenUVR, please watch the following video clip. video demo of the OpenUVR system. And through the video, you have just seen the OpenUVR can be set up with just any head-mounted device. And though not reported in the paper, we're going to show you here that the current version of OpenUVR can also support sensors. Okay, so there are several pitfalls in the conventional thinking of VR systems that were clarified in our paper as well. We're going to first take a look at the graphics card aspect. And so there's a fallacy that graphics card matters. Well, we were able to measure a difference in latency between the mid-end GTX 1060 and high-end RTX 2080 graphics card. Both can perform consistently at 90 FPS and full HD. Therefore, on this matter, we conclude that anything more advanced than a mid-end graphics card would be unnecessary. Also, after discussing the amount of latency involved in video compression, you may be inclined to think that this process is unnecessary for low latency network. However, without compression, the large amount of data would not only incur network latency, but latency in memory copying as well. In our paper, the transmission of 5.39 megabytes of raw data took 1.1 milliseconds. The encoded frame, on the other hand, only took 250 nanoseconds. In our example, video compression only takes 3.72 milliseconds in total, and that could be improved by developments in hardware acceleration. Finally, as discussed before, the next generation millimeter wave is in fact not a good approach to developing wireless VR systems. Wireless network transmission is an insignificant part of end-to-end latency, and millimeter wave is heavily affected by the environment, typically requiring line-of-sight communication to achieve the claimed high bandwidth, and thus it restricts mobility by a great amount as well. To conclude, I would like to focus the attention of the systems and architecture community to VR technology. The source of latency in untethered VR systems is in fact its well-layered system overhead. Our paper demonstrates the possibility of removing this layering overhead by applying a few techniques on commodity hardware components. By making our project open source, we hope to garner support from the community to investigate potential optimizations to VR systems. Systems design is necessary where wireless technologies fail to address all of the issues. And with that, this project was under the support from NSF, NC State University, and UC Riverside. I would like to thank you once again for being here, and if you are interested, please do not forget to check out our open source project at this link. Thank you very much.